Okay, these are the solutions for test 1, Math 191. We are given 2 points, and we are asked to find the average rate of change between different points, and then find the slope and find the equation of the tangent line. So I created the slope formula for the average rate of change, or the secant line, if you'd like, between P and Q. And this is it, y2 minus y1 over x2 minus x1. I entered it in the graphing calculator, carefully with enough parentheses, around x minus 7, and of course around x minus 8, and then second in table, and I punched in the numbers I needed, the 7.9, and so on and so forth, and I copied them here. After that, I used the limit. I didn't want to guess. I also wanted to show you how to create this. So in part B, I just determined the limit of that. So determining the limit of the secant line, I will determine the slope of the tangent line. So I found the least common denominator. I simplified the least common denominator. This is 7 minus x. And I factored out the 2 first. That's what I did. Factored out the 2, and then I simplified my life very much. And 2, and the numerator becomes x minus 8 after I factor out -1. And the denominator is flipped, and the denominator here also factored out -1. So when you plug in 8 now, this is 1, this is +1, so this is 2. And then I determined the equation of the line, of the tangent line, with the slope of 2, and the ordered pair 8, -2, 8, -2 in the slope point form. And then this is 2x minus 16, and I bring to -18. So this is final. Next, in problem 2, we were asked to look at a graph and analyze the graph at different points. So obviously these are both points called removable discontinuities. This is a jump. Here from the right hand side, the limit is 5, and from the left hand side is oscillating, so it's D and E. So I explained removable discontinuity because the limit from the left and the limit from the right, they are equal to 4, but they're not equal to the function value at -3. The jump at 0, so the jump at 0, the limit from the left is 1, the limit from the right is -1. So I presented those. So the limit from either side is D and E. At x equals 2, again the same thing, it's a removable discontinuity. The limit from the left is 2, the limit from the right is 2, but not equal to the function value at that point. And at 5, the limit from the right is 3, but the limit from the left is D and E, therefore the limit from either side is D and E. This was a piecewise defined function. We were asked to graph it. I changed all these 3 intervals into inequalities into interval notation. I realized that the domain is -infinity to infinity. And then I presented the important points, 0 and 1, bracket on the left, parenthesis on the right, parenthesis on the left, bracket on the right. And I established which function goes where. And I plugged in some numbers, -1 and 0. And then 0 and 1, this is a linear function, and then 1 to infinity in the natural log. So 1 over e was -1, 1 over e kind of difficult to show. Then at 0 on the left, the limit is 1. 0 on the right, the limit is -1, straight line. And now the natural log function is this, but of course I have to pick it up at 1 to infinity. So as we see here, the limit from the left and the right are the same, so the function has a limit from either side. But here is a jump, so the limit from the left of 0 is 1, and the limit from the right is -1, as we see them in the table. Therefore, the limit from either side at 0 is D and E, Everywhere else, the function has a limit from either side except at 0. And the range is from -1 to infinity. The next problem was asking us to use the information and create a function, an example of a function. So I put everything in the table, the limits from the left and from the right, 0 and 1. -1 at -1 is 4. The limits from either side are 3, so this is a removable discontinuity, this is a jump discontinuity, and at 2 the function is 2. So at -1 the function is 4, at 2 the function is 2. The limit here is the same, so this is a removable discontinuity, but here the limit on the left is 0 and the limit from the right is 1. These were some limits to look at. The limit from the right-hand side of 0, sine is 0, and natural log from the right-hand side of 0. As we know, here's the graph of natural log again from the right-hand side of 0. So it's -infinity. Here, cotangent, so pi from the right means the second quadrant. This is pi from the right. This is pi, and pi from the right is in the second quadrant with numbers lower than pi, angles lower than pi. So this approaches pi, but cotangent, as we know, cotangent x is cosine x divided by sine x, and sine x is 0. But it's on the positive side because sine is positive in the first and the second quadrants. But cosine is negative here and here. So cosine is negative, negative in the second and the third. So cosine is negative, sine is positive. That's why we get -infinity. Here it's a limit of 0 over 0. I have to rationalize the denominator using the conjugate. I of course present this in the descending order, factoring out -1. I know that when I plug in 2 and I get 0 over 0, the culprit is x minus 2. X minus 2 is the factor that I want to get rid of. So x minus 2, I rationalized. When I multiply these two, a minus b times a plus b, I get x plus 2 minus 4, which eventually changes into x minus 2, which will factor and simplify the top. So the final answer is with minus this, but when x approaches 2, 2 plus 2 is 4, the square root of 4 is 2, 2 plus 2 is 4, with minus in front, the limit is -4. The next one is a rational function. I have to change it into 1 over 4 plus x, 1 over 4. Find the least common denominator, which is 4 times 4 plus h. The top needs a 4. The top here needs a 4 plus h. I distribute. 4 goes away. Of course, as expected, all terms without h have to go away, and then h over 4 plus h. I flip. I simplify the h. When h approaches 0, I have 4 times 4 is 16 with minus in front. So the limit is -1 over 16. Next, here we will have to find the least common denominator. I factor out 3 from both. So I have 1 over x, and I have to factor the denominator, which is x times x plus 1. So the least common denominator is x times x plus 1. So only this fraction needs at the top to be multiplied by x plus 1. X plus 1 minus 1, all terms. Without, in this case, just 1 minus 1 go away. And eventually, of course, x with x will be simplified. So I have 3 in front. Limit 1 over x plus 1. When I plug in 0, I get 1 over 1 times 3 is 3. Here I have to simplify this function, so I start with x plus 2 in absolute value, which has these two options for this and this. And now the entire function, which is basically this one, x plus 2 in the numerator, x plus 2 in the denominator with 5, I have 1/5 for greater than not equal to, because x plus 2 is in the denominator, x cannot be -2. The other option is with x plus 2, negative x plus 2 at the top, simplifies -1 over 5 when less than -2. I determine the limit from the left of -1, I get -1/2. I determine the limit from the right of -2, I get -1/5, positive 1/5, sorry. So therefore they're not the same, so the limit from either side is d and e. Last one here is basically the squeeze theorem. So I know that sine is a bounded function between -1 and 1. I'm allowed to multiply by x to the fourth because it's never 0. This implies not equals 0, and it's positive. So I multiply. This is the first hypothesis of the squeeze theorem. And now I apply the limit to this. I apply the limit to this. I realize they both exist and they're equal. So the two hypotheses of the squeeze theorem are fulfilled. Therefore, I can conclude that this is 0. The same thing with number 6. It's just that the first part of the squeeze theorem is already given. I don't have to analyze this. It's given to us. So I determine the limit from the lower function. I determine the limit from the upper function. They have to be the same. They equal 7. Therefore, from 1 and 2, by squeeze theorem, I conclude this. Now, problem 7, the epsilon delta definition. I have to start with, for every epsilon greater than 0, there is a delta greater than 0, such that every time I pick x between close enough to 2, of course positive, not 2, this means that I cannot pick x to be 2. This answer here has to be greater than 0, not 0. The absolute value is always positive, but because there is no equal symbol, it tells us that we cannot pick x to be 2. So every time the distance between x and 2 is less than delta, the distance between the function and its limit has to be less than epsilon. I start at the end. I have to combine like terms. I have to factor on -3. I have to show that I'm using the property that the absolute value of a product is the product of absolute values. I change the absolute value of -3 into 3. I divide both sides by 3, and that's our delta. Reverse the steps to show that delta equals epsilon over 3 works. Here, we were asked to find c so that this function is always continuous. I know that these are polynomials. They are continuous everywhere. But now what happens at 3? The limit from the left has to equal the limit from the right has to equal f of 3. Limit from the left is from the first function. Limit from the right is from the other function. And f of 3 is the same here. So it's just, these two must be the same. So therefore, when I plug it in, I get the left-hand side. So when I plug in x equals 3 here, 9 times 2 is 18c minus 24. And when I plug in 3 here, I get 3 minus 9c. 3 minus 9c. I move 9c to the other side to get 27. I move 24 to the other side to get 27. So divide c is 1. I plug it back in, and this is the function that is continuous everywhere. Continuous on negative infinity to infinity. Okay, so f prime, we're asked to find the derivative of the function with the definition of the limit, definition of the derivative, which is the limit of the difference quotient. I plug it in, so it's 2x plus 2h minus 3 over 1 minus 5x minus 5h minus the function over h. So I found that the least common denominator must be the product of these two. So therefore, the top of the first fraction needs to be multiplied by the opposite one, the one that it does not have. The same thing here, 2x minus 3 has to be multiplied by the opposite, what it does not have. So 1 distributed here, negative 5x distributed here, minus, careful, 2x distributed here, and positive 3 distributed here. So I got all these at the very top. 2x plus 2h minus 3 minus 10x squared minus 10xh plus 15x minus 2x plus 10x squared plus 10xh plus 3 minus 15x and minus 15h. Everything went away after you simplify and you only have 2h and minus 15h, which is negative 13h. As expected, all terms without h must go away. And I flip 1 over h and I simplify and I get this. So this is the derivative of the function. Oh, I didn't copy it here, sorry. Okay, now here we're asked to show that there is a solution. So I created the function. I said it's continuous everywhere, anywhere where x plus 1 is positive, because natural law cannot be applied to anything but strictly positive numbers. So I found an interval 0, 1. I put the function in the graphing calculator. Natural log x plus 1 minus 2 plus 3x, and I plugged in numbers. So I plugged in, I didn't mean that, I meant this. So I plugged in 0 and then 1, and I saw that the function changes sign. Knowing that it's continuous between 0 and 1, and it changes sign, I'll say, by the intermediate value theorem, and here are the answers. For f of 0 is negative and f of 1 is positive by IVT. Since the function is continuous on 0, 1, there must exist a c in the interval 0, 1, open, closed here, open here, such that f of c is 0. Finally, two more limits here. X approaches negative infinity. So I factor out negative 1, x, that's the degree of the top, negative x. So I have 2 minus 3 over x in parentheses. Here I realize the degree underneath is x squared. I pull out x squared, and I have 1 plus 2 over x squared. I apply the rule that says that the square root of a product is the product of square roots, but now I have to be very careful because the square root of x squared equals negative x when x approaches negative infinity. So this turns into negative x. I will eventually simplify the negative x with negative x. And when x approaches negative infinity, this piece goes to 0, this piece goes to 0, the whole thing goes to 2. So y equals 2 is a horizontal asymptote at negative infinity only. Same thing here, it's infinity over infinity, indeterminate case like the previous one. But here I will factor out e to 2x. So 4 minus, when I divide or pull out e to 2x, e to negative 2x divided by e to 2x becomes e to negative 4x. How do I know? You can put it back in. This times this is this times this, copy the base, add the exponents. In the same way I factor out e to 2x in the denominator, I get 3 minus e to negative 6x. Negative 4x divided by e to 2x will become e to negative 6x. So the answer is 4/3 because this will go to 0, this will go to 0 when x approaches infinity. So 4/3 is the horizontal asymptote at infinity. So here we are given this and we're asked to find what is the limit as x approaches 1 of f of x. So this is a tiny little trick. We multiply and divide by x minus 1. This just the top. So we separate into and rearrange, putting an x minus 1 in the denominator here, and then away from it as a product, limit of this, because I have it, it's 8, times limit of this. So we know that this is 8 since it's given to us, but when I plug in 1 here, I get 0. So if this is 0, 8 times 0 will be 0. Good enough. Now I can go back from the beginning and say that the limit of this, because this is 1, is 0. Okay, if that is 0, then I can separate it into the limit of f of x as x approaches 1 minus 3, the limit of 1, or the limit of 3, which is 0. So I just copied this by applying limit to this minus limit to this, limit law. So then this is 3, goes to the other side, so then therefore the limit of f of x as x approaches 1 is 3. Final extra credit, if the two limits are 0, will this always exist? No, not necessarily. 0 over 0 has chances to exist, but there is no guarantee. So we cannot say that that limit exists for sure. Thank you.